A tank of water in the shape of a cone is leaking water at a constant rate of 2 cubic feet per hour. The base of the radius of the tank is 5 feet and the height of the tank is 20 feet. I'm just going to draw a picture real quick. So I know the radius is 5 feet. The total height of the tank is 20 feet. And I want to know at what rate is the radius of the water changing when the depth is 6 feet. So let's break this down here. The first thing I notice is, if I'm talking about similar triangles, I notice that the ratio of the radius to the height will always be 5 to 20 or 1 to 4. So if I multiply both sides by h, I can get the relationship that my radius is 1/4 my height, or I could find the relationship that my height is 4 times my radius. I don't know which one I care about yet, but they're both equally useful. So I want to label the information I have in my picture. This leaking water at a constant rate of 2 cubic feet per hour, that's telling me what the rate of change of my volume is. The rate of change of my volume is -2 cubic feet per hour. Now I know that's my volume. A dead giveaway is that the feet is cubic feet, which is 3 dimensions, and that the water is leaking out means that it's a negative rate of change. So the volume of my water is decreasing over time here. It tells me that I want to find what's the rate of change of the radius of the water. So I'm tasked in finding dr dt, and they tell me that the depth of the water currently is 6 feet. So if I write an equation to relate these variables, my volume equals 1/3 pi radius squared times the height. That's the volume formula for a cone. I've got a couple of issues here. I'm looking for dr dt. So I want to get it so that on this side of the equation, I only have r, because I eventually want to take a derivative and end up with something that has a dr dt in it, and then rearrange the equation to solve that. So I'm going to make a substitution for h here. I already know earlier that my height is also the same thing as 4 times my radius. So what I'm going to do is I'm going to substitute in. My volume is 1/3 pi r squared times 4r. And if I rearrange this a little bit more, I could find that if I bring that 4 out in front, this could be 4/3 pi times my radius cubed. Okay, now we're getting somewhere. One thing I could look at is that if I take the derivative here, right, dv dt, I could implicitly differentiate this side. 4/3 pi, and if I bring down the 3, using a chain rule here, subtract 1 from the exponent, and multiply by my inside function, which is dr, which is just r. Remember, r is a function of time here, right? As time goes on, r is going to change, so I need to remember to multiply by that dr dt. There's a problem here, right? If I try to make substitutions, I know who that guy is. I'm looking for that guy. But r is still an unknown, so I would have 2 unknowns in this equation. So we've got to go back to the drawing board. We got to ask ourselves, why did they tell us that the height was 6 feet? Well, I know that my radius is equal to 1/4 of my height. So if I apply this relationship real quick over here, technically if I know the height, I know the radius of the water, and if I know the radius of the water, I know the height. So I know, like, the height of the water here is 6, and if I multiply that by 4, I get 6/4, or if I reduce that, I get 3/2, or I like decimals sometimes, the radius of the water there is 1.5 feet. So that's who I'm going to substitute in for r over there. So I can make dv dt -2. I'm going to reduce the 3's here just to make my life a little bit easier. 4 pi times my radius squared times dr dt. Now, you should notice dr dt is just being multiplied by a constant. So what I'm going to do is I'm just going to divide everything over. So I'm going to divide 4 pi 1.5 squared, and I'm going to divide 4 pi 1.5 squared. So I get dr dt is equal to, I'm going to type that into my calculator, negative 0.07. Think about your units. I'm going to go back. I know everything's measured in feet. I didn't try to trick you with the units. And my time interval here is hour. So negative 0.7 feet per hour is how fast the radius of the top of the water is decreasing here. So what I did is I made a substitution into my volume formula to eliminate one of my variables because I cared about the rate of change of r. Now, if I wanted to plug back in and find the rate of change of the height, I could. I could do the opposite and just plug in my other relationship. Rather than eliminating r, I could write this as v equals 1/3 pi. Instead of r squared, I could write 1/4 height squared times the height and do the same process and end up with an equation that would help me solve for dh dt. So it really just depends on which rate of change I'm looking for which variable I'm going to eliminate.